simple support there. There, you have a point load here, here. Those dimensions, it's 1, it's 2 meters. 1, and then we have a UDL which runs along 3/4 of the beam. That's 4 kilonewtons per meter. This one is 20. This one is 10. Okay, so summing the forces, we have RA plus RC, so that's A, B, C, D, equals, well, 20 plus 10 plus 4 kilonewtons per meter by 3 meters is 12. So that's 42 kilonewtons. Okay. Take moments by point A. We get 3 times RC is equal to, 1 by 20 plus 4 by 10 plus 4 times 3, and that UDL is assumed to act 1.5 meters along. So that's equal to 20 plus 40 plus, getting ahead of myself there, 18, which is 78 kilonewtons. Okay, so RC is 78 divided by 3, so 3 into 7 is 2 so 26 kilonewtons. And RA is 42 minus 26, 16. Okay, so if you recall, when we were doing these before, again, we'll just roughly sketch it out. So the shear force diagram, we're up, RA is 16, so we're up 16. The UDL over 1 meter brings us down by 4 to 12. We then have a sudden downward force of 20. That brings us to minus 8. And then we drop another 8 because of the UDL, minus 16. The reaction at C was 26. We were up to plus 10. No UDL here, so the line is horizontal, and then down to 0. Okay, so that's what it looks like. So we'll just get the areas of those shapes. The average height there is 14, so the area is plus 14. Here the average height is 12 and it's 2 meters long, so the area minus 24 in their kilonewton meters. And here it's just 10 by 1 plus 10. Okay, so for the bending moment, remember when it's under a UDL, it has a parabolic shape. So, and it's 0 because they're free ends or they're simply supported. So it's going to go up to a maximum of plus 14. Then it's going to go down. So it's dropping plus 14 minus 24. So when we get to here, it's dropped by 24. So it's at minus 10 and it's going to have this parabolic shape. It's going to look like that. Okay. And then for the last bit, the area is plus 10, so it gets us back to 0, but it's a straight line this time. Okay, so the maximum positive bending moment is plus 14 kilonewton meters at B, and the maximum negative bending moment is minus 10 kilonewton meters C. So if we were to draw the shape of the beam, At point B, does the beam sag or hog? Okay, so is it sagging or hogging point B? So let's do a quick poll there. So point B is here. So is it sagging down? Think about the loads that are on it. Okay, yeah, that's pretty clear. And then at point, so I'll stop that one. Then at point C, is it sagging or hogging? So at this point here, what's it doing? Again, A is sagging, B is hogging. Yeah, okay, pretty clear. Okay. Okay, so in fact, again, this is just a simulation. So that's what the beam does there. So you can see it clearly, it sags at point B, it hogs at point A, and it drops down quite a bit at point D. So you can see how it looks. Okay, so okay, so if we look at part C of the question, let's go back to the question. So we have a few minutes left. We'll just take this. Question. There's the question. Okay, so if we go down to part, so you would have got 8 marks for your shear force diagram, and you would have got 6 marks for finding the maximum position and magnitude of the maximum positive and bending negative moment. So you're asked for both. Okay, now let's look at the thing here. So you're told the section is, it's a T section with an I value of 12 by 10 to the 6 millimeters fourth. The total depth of the beam is 90, and the neutral surface is, you can see there, it's kind of 2/3 of the way up. Okay, so that means that for any given bending moment, the stress at the top is going to be, well, the stress at the bottom is twice as far away as the one at the top, so it's going to be twice as much. So you're asked to find the maximum magnitude of the maximum tensile and compressive stresses in the beam. Okay, so if you look at your shear force diagram, or your bending moment diagram, you've got a positive and negative value there, which are kind of close to each other. So you can't just take it for granted that one is bigger than the other. I mean, if the top one was huge and the bottom one was tiny, you might do that. But if you take the beam section, okay, that distance there is 30, and that distance there is 60. So you kind of have to work them out, okay? So your I value you're given, I is 12 by 10 to the 6, isn't it? Yep. So at point B, top stress is my over I, which is 14 by 10 to the 6 Newton millimeters, by Y, which is 30, over the I value, which is 12. And so that's a minus value. So Y is measured that way. Okay. So the stress at the top at point B is compressive, and it's minus 35 if my maths is correct, megapascals. Bottom stress at point B is, again, the bending moment is the same. This is now plus 60, and the I value is the same, so that's just double, so it's 70 megapascals. Okay. And then at point C, Okay, so the bending moment there is minus 10 by 10 to the 6 Newton millimeters. So the top stress at point C is minus 10 the bending moment, minus 30 for Y and I value. And that works out at 25. Tensile. And the bottom stress, point C again, is minus 10 plus 60 with the I value. Okay, it's twice as far away. The sign has changed, so it's minus 50 megapascals. So the answer there is that the maximum tensile stress is 70 megapascals. Bottom at point B, and the maximum compressive stress is minus 50, and that's at the bottom. That's at point C. Okay, so if you think about the way the beam is going to behave, the beam is going to sag, and then it's going to come up and do that again. Okay, so we're going to have compression here and tension here. We're going to have tension here and compression here. Okay, so that's how it works. So that's an interesting one because it shows that if the center is a good bit away from the kind of middle, then you have to just be careful about positive and negative bending moments because you don't necessarily know in advance where everything is. Okay, I'll get you to do one more question maybe tonight. We'll look at it tomorrow, and then we'll think about the next little bit of the course. So if you can do 2020 question 5. So I'll just pop this out. Okay, so come down to me. Okay, this is a slightly unusual paper. Okay, another one of those questions there. Same type of thing. Question 5 there. Section is a kind of a hollow rectangular section, but the hole is not at the center. So you have to treat it as the outside minus the inside, and you work from the top or the bottom. So just have a go at that, and we'll do that tomorrow. Okay, so that's it for today. Thank you for your time, and we'll see you at, what is it, 10 a.m. or a couple of minutes past 10. Okay, so if you can, please have a go at that one. It's